welcome to my channel, A Woman in Physics. Last weekend I've been at the Technical Collection Dresden, which is a small but very nice and unfortunately also quite unknown technical museum here in Dresden. And in this museum there are tons of hands-on experiments where you can actually try lots of mathematical, technical and physical stuff out for yourself. And at one place I stumbled in particular across a very interesting pendulum that I want to show you today.
So what do we have here? Basically 13 metal spheres hanging on threads. They do not touch one another and they all have the same mass. But what happens if we set all of them in motion? To that aim, we take this blue board and lift it up. Hence, the spheres are raised as shown in this scheme in a side view. However, all the spheres hang on threads of different lengths. And you can see already that it depends on thread length how large the angle phi is by which a sphere is deflected if the deflection distance x is always the same. This relation between thread length L and angle phi can be calculated easily as presented here using the mathematical definition of sine. We have the pendulum length L vertically in the relaxed state and under the angle phi. In the latter case, the sphere is raised by a height h and moved to the right by a distance x. According to the very definition of sine, in a right-angled triangle, sine of phi equals opposite side divided by the hypotenuse. Hence, the angle phi can be calculated from L and x. If we assume, for example, that the sphere has been moved by about 5 centimeters, which is 0.05 meters, then the relation follows like this. And the region of our experiment, where L is somewhere between 30 and 60 centimeters, in this region phi is very similar. There are no extremely large angles, say angles tending to 45-90 degrees, or extremely small ones that are not even visible. So let's go to the experiment. All spheres have been moved by the same distance x. And if we have a look behind the board, then yes, all spheres are still here. Now, if we lower the blue board abruptly, the pendulums start swinging. At first, nicely synchronized, but then everything gets mixed up. Did you see that? For a moment, every second pendulum was synchronized in their motion, but now they are again in total disarrangement. There, for a moment, they were nearly back to the first second of their dance, and again, just a moment later, they are not. So, what's happening here? We already saw that the pendulums swing by angles that are in a range very close to one another. However, in this range of, say, below or around 10 degrees, the sine of the angle can be approximated by the angle itself. So, sine of phi equals phi. Now, you may ask, why is this important? And the answer is probably rather simple for a physicist or a mathematician or an engineer. For such angles, the period of the motion, that is, the time for a complete oscillation, a swing to one side to the other side, a full swing, can be approximated by t0 equals 2 pi times the square root of L divided by g. Now, while I've been talking about how to calculate pi in a, let's say, creative way in a previous video, we have a new constant here, g. And g is a really interesting constant. It is the gravitational acceleration. However, it is not a strictly universal constant everywhere on our planet. In particular, at different points on Earth, objects fall with different accelerations, somewhere between 9.76 and 9.83 meters per second squared, depending on the altitude and latitude of your location. The conventional standard value, let's call it like this, that is used for calculations is commonly 9.81 meter per second squared. So we can plot the period of the motion as a function of the pendulum length, as shown here. And I suppose the different swings of the different pendulums become now very clear. This experiment was exactly designed such that we can see the effect of a variation in pendulum length. And with that, I will leave you for today to the relaxing swinging of the pendulums.